I used to be a music teacher, and I came to a sort of impasse with my school on a philosophical point about how you should treat children. And so I came back out here and I took a mindless job in the lab where I had worked before. Then 3 years later, this material, nitinol, came along, and it's as if I was waiting for that my whole life. This has been the main shop and the main development effort to progress the idea of nitinol engines, which are also known as the Banks engine, because I'm Ridgway Banks, and I made the first one in all innocence over 30 years ago. And much of that has taken place here in this shop, which is a one-room operation in Point Richmond, California. Here is a nitinol wire. Nitinol is a nickel titanium alloy. What happens is that on cooling, it's very easy to bend the wire out of shape as long as it's kept in the cool region. But when you reheat it, it goes back to the crystal structure and the shape that it had before you did this to it. It took 30 years to appreciate that these wires can do a great deal of work, but they have to do it in their own terms. They don't respond well to being repressed. When they're ready to go, they want to go. And if you allow that to happen, they will become more and more adapted to their temperature cycle and more efficient, and instead of wearing out, they get better. It was just a purely playful fooling around with types of motion, and so it was not at all planned. But in 1973, the nitinol engine came along, and I was giving press conferences.
This giant complex of buildings overlooking San Francisco Bay is the Lawrence Laboratory at Berkeley. For some years now, a small group of scientists attached to the laboratories have been investigating this, a curious metal called nitinol. It has certain anomalous properties not yet fully understood or explained. It's caused considerable interest, it has generated some controversy, and it now seems that in a world searching for new sources of energy, it may have profound consequences.
An engineer at the laboratories, Ridgway Banks, set out to build an engine to harness this. In a small workshop across from his office, he designed and built a wheel with nitinol loops hanging from the spokes. He calculated that if he filled a container with cold water and another with hot water, the loops of nitinol, moving from one bath to the other, would bend, then spring back, and that the sudden spring of the nitinol in the hot water would drive the wheel around, thus becoming the world's first solid-state heat engine. He was right.
That picture was taken the day the first engine first ran, and it appeared on the cover of an international science journal called Die Naturwissenschaften. It caused quite a stir because this was 1973, and energy and renewable resources was becoming a hot issue, you might say. And that's the original engine, and that's the King of Sweden. He was on a visit, and they were delighted to have something they could show him that wasn't so technical that he couldn't understand it. My boss hired me originally in the early 1960s. even though I had no scientific credentials at all. He hired me because he was a very serious amateur clarinet player. And my thesis in school was a clarinet sonata. And so we used to get together on my birthday and play that in varying degrees of sobriety. When I came back in 1970, he remembered and hired me back. There isn't much to see upstairs, but there's an organ up there. And I think it still plays. I haven't tried it for a year. I'll take my hat off. Maybe it doesn't recognize me with the hat on. Play is the work of childhood. That's the playfulness settled in. Hey. Okay. It was, to many people, not clear that you had to have an organ in a machine shop, so I think that this counts as a kind of pioneering proof. Probably came up with this in the early 1980s, perhaps even the late 1970s, because the original engine had been named after me. We were calling it the Mini Banks engine. The idea behind this was to try to demonstrate how the shape memory of a wire that's been bent could power a machine that looks like an engine. And this is as simple as I was able to come up with. I don't even know that it sold more than a dozen, and mostly to people who were sympathetic to the project to begin with. It's mostly good for what it's doing right now, making people think. In the early days, the results were very inconclusive. Some machines were built that got better, others got worse. There didn't seem to be any rhyme or reason. Eventually, we developed a system which is basically an upside-down spring that has the characteristics of a spring in reverse. That instead of starting easy and getting hard, it starts hard and then gets easy. It is a tricky process and very sensitive. One of the things about nitinol that I've learned to appreciate is it's unpredictable. And that's, you can't control it. You let it tell you what it wants to do. The spirit of this thing, when it's going well, is best reflected in a comment by Pablo Picasso. He was asked which of his paintings was his favorite, and he said without hesitating, the next one. And so the new machine is based on heating by immersion in a hot fluid and then cooling in air, so that we don't need cold water anymore. Just air cooling is enough. There's a tremendous amount of energy that goes to waste that we don't even notice because it doesn't fit our definition of energy. It's not impressive, it isn't fast, it isn't loud. It just gets the job done.
This is a technical communication to interested members of Congress on recent development in the status of nitinol heat engines. This is a solar-powered pump which consists of a solar collector, a nitinol engine which is contained in this blue box, and a water pump behind the apparatus.
I think that nitinol will open up once the word gets around that it really does work.
An unusual feature of this engine is the fact that it contains no valves, no seals, no high-pressure systems of any kind, no crankshaft, no gears, no power shaft, no flywheel, virtually no component normally associated with conventional engines.
The practicality is terrific, and it happens now at a time when we really are concerned about using high-quality energy fuels. It's very cheap. The components are nickel and titanium, the 9th and 11th most abundant elements on Earth.
The alloy itself has been around since the 50s, but it's only inventors like Banks who have tapped its power. Strands of nitinol, dipping from warm to cold, give off enough force to turn a flywheel. The result is cheap, clean energy.
Engines based on this material or materials similar to it could be used to turn generators, to run pumps, to run refrigerators, any of the uses that we have for conventional engines. This is a 50-pound flywheel, and those less than 3 grams of nitinol are going to power the flywheel now and run a small generator.
It's not flashy. It's not dangerous. Anyone who associates those qualities with something in the energy field that would make it interesting to pursue will not be attracted to these very kind of mild-mannered machines. It's true that if you treat nitinol insensitively, shock it, make it do work when it's trying to do its own personal housekeeping, then it will deteriorate. It will wear out like everything else. But if you let it alone, let it be self-regulating, then apparently it goes on to limits that have yet to be established.
It has not been supported by any major funding. It's been a small operation from the beginning. And that was why I think that when I told Banks go ahead, it was so important to him, because it was I wasn't able to give him a large quantity of money to do it, but I was able to encourage him and to go ahead, and that was about all I could do. But it is important that people are working on these things, you know, and I would like to see more of it done.
Nitinol is highly individualistic material. The outward appearance of two wires can be very similar and they're indistinguishable, but internally, the structures that make the difference in the way the wire behaves can be quite different. It's like snowflakes. They say that no two snowflakes are alike. Well, for the same reason, no two nitinol wires are alike, because the arrangement of crystals in there is very individual from wire to wire. What took 35 years to learn was let the wires do their own thing, but don't ask them to be a member of a group. If you have the forbearance and the respect for the materials, wonderful things develop. It has a lot to contribute in terms of taking low temperature heat and converting it to mechanical work, but on its own schedule, and that's what has taken a while to appreciate, and it was very well worth the trip. I know that there is an appetite, very important appetite component to what draws those molecules together. According to classical physics and the theories of thermodynamics, the world should have worn down to a sludge, and a lukewarm sludge at that, a long time ago, and yet it somehow doesn't. There is a playfulness about this, which is offensive to a lot of people. That's an early nitinol engine. Nature, and particularly when you get to be in the subject of energy and mechanics, is not really supposed to be playful. It's supposed to be business-like.
It's not getting any better.
It's very hard to maintain the position that something like wind is all business and not playful. But when I look at this tree, this Chinese camphor tree, I see tremendous variety of things going on, and they're not all linear. They're not all consistent. There isn't a great deal of conformity. Wind is terribly complex. Wind does not like to be trapped or circumscribed or enclosed or pushed into a corner. There's a whole universe of conditions that we can't observe directly, we can't quantify, and they absolutely defy any effort to put them into a rational framework. And yet it keeps things going. There's a little gadget which is powered by a nitinol wire, and that has been running at 17 cycles a minute for close to 10 years, and it is approaching, if it hasn't already passed, the 81 million cycles mark. The mechanism that it lifts is wearing out. That's just a plastic drinking straw. I don't want to touch it because in its own crude way, it's an unmonitored lifetime experiment. But it gives me a great deal of hope. I think socially, economically, ecologically, and philosophically, if I may, the time is really right for this material to come into its own.
But with all that going for it, why is nitinol still so slow in catching on?
It doesn't behave according to your expectations, so that there is a natural skepticism about this. Is this really worth doing?
So far, the world has yet to beat a path to Ridgway Bank's door and his nitinol-powered machines, but the inventor has no intention of giving up. It's mostly a question of sitting back and waiting for the rest of the world to catch up with the idea.
You can't make a bunch of wires behave like a single congregational parish. They are individuals. Each nitinol wire in its own coonskin cap, rudely refusing to conform.
It's quite an exciting feeling to have that thing spring to life in your hands.